This video contains two more solutions of problems on finding electric field from potential field. The first one is very simple. Potential field V is given. So we have to find electric field strength at given point M. So we know that electric field is given by negative gradient of potential. In Cartesian coordinates, del V can be expanded as dou V by dou X minus dou V by dou Y AY minus dou V by dou Z AZ. So three partial derivatives are there. So in the first one, we have to differentiate V with respect to X. Let us substitute for V from the given problem. So there is 3x square y plus 2y z square plus 3x y z a cap x. So this forms the x component. Similarly, we are having the y component of electric field, which is given by the differentiation of 3x square y plus 2y z square plus 3xy z ay cap minus dou by dou z of 3x square y plus 2yz square plus 3xyz az cap. So in this case, we have to be careful. In the potential field, we should not treat this first term as x component, second one y z, and last one the z component, because the complete equation represent a scalar function. So in the next step, we shall perform the differentiation first with respect to x. So we get here the first term x square is 2x, so it is 6xy. In the second term, no x, so it is going to be 0. So in the last term, there is x here. Differentiation is 1, so we have 3yz ax cap. Similarly, the second one, with respect to y, here is y, whose differentiation is 1, so we get 3x square. And in the second one, similarly, plus 2z square. Here this bracket not required. In the last term, differentiation of y is 1. We get 3xz ay cap. And in the last one, with respect to z, first term do not contain any z component, so it is 0. Second one, z square is 2z, so it is 4yz. The last differentiation of z is 1 plus 3xy a cap z. So the differentiation is over. All three components of electric field are obtained. We have to simplify if needed. Let us see what happens in the next step. That is E is equal to, here any simplification possible, let us check it, minus of 6xy plus 3yz ax cap. Here it is minus of, no changes possible, 3x square plus 2z square plus 3xz ay cap. The last one is 4yz plus 3xy az cap. Now the question is to find electric field intensity at the point specified. So let me copy the point. It is 1, 2, minus 1. 1, 2, minus 1. So at the point M, 1, 2, minus 1, E would be given by, substitute x, y, z values here. 6 into x is 1, y is 2, plus 3 into y is 2, z is minus 1. This is x component minus, similarly 3, x value 1, 2 of z value minus 1, plus 3 into x is 1, z is minus 1. Ay cap. In the last term, y is 2, z is minus 1, plus 3, x is 1 and y is 2. Az cap. So the electric field now reduces to, so this term is going to be 12 and this is going to be minus 6. 3 2s are 6 to minus 1, minus 6. So 12 minus 6 is 6. So one more minus is there. So it's going to be minus 6 a cap. Similarly here, second one, this is 3 minus 1 square is plus 1. This is going to be 2 and this is going to be minus 3. So both gets cancelled out. You will be left with the 2. 2 into minus 1 is minus 2. So it's going to be minus 2 ay. The last step, it is going to be minus 8 and this is 6. So we're going to get minus 2, so minus into minus plus 2 a cap z. This is the electric field at the point M, volts per meter. And if you would like to find the magnitude of this electric field at the specified point M, we can go for one more step, 6 square, 2 square and 2 square. 36 plus 4 and plus 4. So it's going to be 44 under root volts. This makes the solution of the problem. So we have found electric field strength at the given point. Now we shall continue to second numerical of similar type, which is here. Let me designate it as problem number 3. This is also similar to the previous one, but we need to find more quantities in this case. So potential field V is given. We have to find electric field intensity E minus del V minus dou V by dou X AX dou V by dou Y AY minus dou V by dou Z is AZ. It's a good practice to write the formula in problem solving. So in the first one, we shall differentiate V with respect to X directly. So V is given here. Let us differentiate with respect to X and put it here. So differentiation with X in the first term is 2X. So it's going to be 4XY. Second term, no X, so 0. So 4XY AX cap. Similarly, with respect to Y, it is 1 in the first term, so it's going to be 2x square. No Y in the second term. Last one is with respect to Z, first one 0, it's going to be minus 5. So minus into minus plus A cap Z. So differentiation of this flow is going to be 0, and this is going to give us minus 5. So that is already one minus is there. So minus into minus plus it becomes. This is our electric field E. And it is required to find electric field at point P of minus 4, 3, 6. So at this particular point, we shall find E, that is 4. One is X is in this problem. So 4 is there. In place of X, we have to write minus 4. So in place of Y, we shall put 3. Minus 2. X square is minus 4 square AY plus 5 AZ cap. This is going to be here minus into minus plus. So it's going to be 48. And minus 4 square is minus square is plus 16. So 32 and plus 5. This is the field at the given point. Volts per meter. Let us see what else is required. So calculate electric field intensity at the point minus 436. It's done. Also calculate volume charge density that establishes the given potential field. So keeping the same potential field V, we have to find volume charge density rho V. So we have to find volume charge density rho V coulomb per meter cube from here. To find rho V, I'm going to use point form of Gauss law, that is the Maxwell's first equation, del dot D, divergence of D. But D we need first. So this is given by epsilon naught E. So just by multiplying E with epsilon naught, we can find D. So we shall go for D is equal to epsilon naught into. We should not use this equation of E. This is the equation of E at a specific point. So we want electric flux density field. So that's why we use the electric field equation. This one. That is minus 4xy ax cap minus 2x square ay cap plus 5 az cap. So in this case, we have to multiply by epsilon naught throughout. Let it be there. Coulomb per meter square. Now we shall jump into rho v, that is divergence of D, which can be expanded as dou by dou x of dx. Look at here, no unit vectors will appear here because it is a dot product, the scalar operation. So dou by dou y of dy, dou by dou z of dz. So you have to differentiate x, y, z components of D. So in the first differentiation with respect to x, so dx. So what is dx? Let us see this match. So it's going to be 4x y into epsilon naught. Similarly, dou by dou y of y component, that is minus 2x square epsilon naught. Differentiate with z, that is 5 epsilon naught. A simple differentiation here. In the first case, with respect to x, we are going to get minus 4y epsilon naught. Here also, differentiation with respect to y, so there is no y term, it is 0 plus. The last one also, there is no z term, that is also going to give us 0. So now finally, we got minus 4y epsilon naught. This is going to be our volume charge density. If you want to find this volume charge density at the point specified, we can use that point, whatever given in the problem, minus 436. Minus 436. So that is, if you want at point P of minus 436, the volume charge density is given by minus 4, y value 3 into epsilon naught. This is going to be minus 12 epsilon naught. If you want, you can also substitute the value for epsilon naught, that is 8.854 to 10 raised to minus 12. So we can multiply these two terms using calculator and get the answer. It is 106.248 pico coulomb per meter cube. This gives the volume charge density. So here, point to be noted is, you can find volume charge density from the D. D is anyhow always available from E. E is calculated from V. So if you know the potential field, we can find electric field, flux density field, and also volume charge. So potential plays a very vital role in this kind of applications. That is the solution of this problem.